Again, I'm Eric Osborne, and this is Jenny Jones, and she's going to explain to us young tableaus in respect of algebra. Thank you.
Hi, I'm Jenny Jones, and like you said, I'm gonna do my project is abstract tableaus, basically finding the relationship between abstract algebra and young tableaus. I worked under Robert Race, which is my mentor. I worked with partitions, which is basically a way of breaking up whole numbers using other whole numbers to equal the sum of the initial number that I started with. I also worked with young diagrams, which is like an exoskeleton of young tableaus, which is what I worked up to. I also worked with symmetry and permutation groups. Symmetry groups are like actions that you can put on objects such as squares or triangles, where you flip them or do reflections and change sides and stuff. And permutation groups is like where you change numbers in place of others. And then eventually I did young tableaus, which are like young diagrams, but they have fillings. My research question was basically to find how many permutations would fit into the requirements of having sets that either have two numbers or have the numbers 1 and 2, and that I could do on young tableaus to make it that they're still young tableaus. So partitions are, again, ways to break up a number using whole numbers to equal the sum of the initial number. Like for number 2, you can see that it says 2 plus 0, and then I also have 1 plus 1. The number of sets for these gets larger as it goes on. Along with partitions, there's also partition theory, which is really important because they connect a lot of math concepts together. What is going on? Okay. So, yeah. Oh gosh. What the heck? Okay. Basically, I wanted to find the number of sets that either had two numbers or used the numbers 1 and 2. In order to do this, I went into doing young diagrams. Yeah. Okay, so young diagrams basically look like this. They're an exoskeleton of young tableaus. The figures that I've shown here are both figures of the number 6. The figure on the left side shows the partition 3, 2, 1. You can see the top horizontal level has 3, and then as it goes down, it has 2 and then 1. The one on the right shows that there's the partition 4, 1, 1 or 4, 1 squared. Again, it has 4 on the top and then 1 block and then 1 block. After that, I did symmetry groups, symmetry and permutation groups, which again are actions that can be put on objects, flipping them, doing reflections. I did this on squares and triangles. So my examples are, I did D, which is one way, which is a diagonal switch, which is where I switch the top left corner with the bottom right corner, which would make a totally different sequence of numbers. And then I also have D prime, which is where I did another diagonal switch, but I did the top right corner and the bottom left corner, and that also made another set. The bottom figure shows the rectangle, no, not the rectangle, the triangle permutations that I did. I have F, F1, and F2. As you can see, F1 is where I changed the top right side with the bottom. F1 is where I switched the bottom with the left side, and then F2 is where I switched the left and the right. I also did rotations, like I had rotation of 120, so for triangles, it would be, I would switch all of the numbers starting with the triangle that has the 1, 2, and 3 for the R0, and then switching those clockwise once, and then for the R240, change the numbers twice from the beginning triangle, and then R0 would be switching all the numbers 360, so it would be the same again. A permutation is a way of changing numbers or rearranging them to take each other's places. I did this with matrices to make a table, which I'll show you later. I made matrices like, so if you had the numbers 1, 2, and 3, and then let's say you had, you switched those around again and you had 3, 2, and 1, that sequence would be called, it would be 1, 3, 1, 3, because 1 goes to 2, 2 goes to 2, which you wouldn't put down, and then 3 goes to 1. I also did that with a whole bunch of other numbers too, but did switch? Oh, yeah. So I have these are the tables that I put the triangles in. They're Cayley tables, and they help show the relation between like figures and stuff. So the one on the left shows the triangles. The one on the right shows the matrices, which is what I showed here. I have the 1, 3 over there too. If you look closely, like let's say you took 1, 3, which is over on the right end over here, and then you also look at the table on the left, in the same place it has F2, and everywhere that there's an F2 on the left side, on the left table, there's a 1, 3 on the right table, so they correspond, which I thought was very interesting. And that could have led to something else, which I wanted to look into. So I went on to making young tableaus, which again, like I said, is like a young diagram, but with fillings. The fillings had to fit a certain rule, which is where from every time when you go from left to right, the numbers have to get bigger, and when you go from top to bottom, the numbers have to get bigger. So figure down in the corner shows a standard filling, which is where you just label them until you can't label them anymore. And then you have other fillings where, like the top left one was the original one, and then the one on the top right one is where I switched 3 and 4, and that's where I am trying to answer my question, which is if I can permute, which is change two numbers, if how many of those I can do with having a tableau where it fits the equation, fits the rule, which here it does 1, 2, 4, 2, 4 is too big. 4 is bigger than 2, and then 3 is bigger than 1, and then the last one I have is 1, 3, 4, and 2, which is where I switched 3, 4, and 2. And if you look from the top left and the bottom one, all I did, in order to get those back, you can either do a triangle, which is where you move the 2 up to the middle square and then move the 3 over and the 4 down to where the 2 was. Or you could do 2 switches. But the one with the triangle was very particular because, like before, it would have been, if I was doing the triangles with the Cayley tables, it would have been a rotation 120. And yeah. So if I were to do future research on this, which I would have to come up with a concrete conclusion, I would need to find a closed form equation, which basically would tell me how many permutations I would get for like a large number. Let's say if I wanted to do like 216, and I wanted to find out how many permutations would only use 2 numbers. I would have to find a closed form equation for that instead of having to like write it out for 2 hours or whatever. And then how many permutations there would be in general, which would be a lot. Acknowledgements. I'd like to say thank you to Excel Energy, AOP Course Foundation, Robert Rage, my mentor, and FSI, for having me here. Okay, you guys have any questions?